Good morning. Today we are going to look at closely the design of transmission system, manual transmission system for our passenger car or commercial vehicle, right? How they are going to be designed. And the basis is what we are going to learn in this particular class. And this particular class is to the context of our learning of longitudinal dynamics of our course vehicle dynamics, wherein we have looked at importantly the expression for dynamic load transfer, and essentially during accelerating condition on a slope, what are the normal loads that are acting at the axle is what first we looked at, and we derived those expressions looking at various external forces acting on a vehicle, passenger car. And then subsequently, we were able to get what is the maximum tractive effort that can be developed at the tire road interaction from the calculated normal loads by the factor called road adhesion coefficient. So the maximum tractive effort that can be developed is limited by the product called mu times W, where mu is called the road adhesion coefficient that we have seen. So your vehicle happens to be front wheel driven vehicle, then it is MEP times WF. If the vehicle is happen to be a rear wheel drive vehicle, then it is MEP times WR. And we were able to deduce from there the important expression for both, whether it is rear wheel drive or front wheel drive, what is the expression of maximum tractive effort that can be developed at the tire road interaction from the free body diagram of your vehicle. Right. So this is what we have first learned in the first lecture, and then we looked at another important requirement of a vehicle is power plant and transmission characteristic of the vehicle. So there is power supplied from your engine of your vehicle, and that power, how much is its equivalent tractive force that can be supplied from the power unit is on one hand. On the other hand, this MEP times W is on the other hand. So there are two values of this. Smaller of these two values will always decide the performance potential of your vehicle. Is what is the first hand everyone should have to understand. And also we have concluded, or we have justified that during low speed requirement, means the vehicle has to grade on a slope. At that time, I require more of a torque requirement than the speed requirement of my vehicle. At that time, the deciding factor would be your road surface factor, MEP times W. On the other hand, in high speeds, when I go, I have my engine power supply would be normally smaller than that of what is that MEP times W that is felt at the tire road interaction. At that time, the power supplied from the power plant is going to decide. So these are the two occasions where one takes the other to decide the performance potential of the vehicle. The one which is taking hand on deciding this performance potential is the lower of these two values, smaller of these two values. So this is what is the second understanding that we have made it in our another lecture. And then we looked at the advantage of having power plant in your vehicle by an IC engine based. Why it is so? So we looked at the power torque characteristics of your petrol engine, and then we have looked at also the ideal requirement for your vehicular application. They are of contradicting results. So the engine as it is, if I have to use it directly, I cannot have the requirement of your vehicle torque speed characteristic, torque power speed characteristic. That is where the role of transmission system that comes. So I can have an appropriate transmission system, and I can have my engine appropriately chosen for to have my maximum speed of my vehicle, and by integrating my power unit along with the transmission system appropriately, I would be able to achieve the ideal requirement. And an advantage of doing this is because an IC engine has got an advantage of having high power to weight reduction, weight ratio. Power to weight ratio, if you look at, that is more in case of an IC engine. That's an advantage. That's why we go in for employing an engine and along with the transmission system. And second advantage is it has got good fuel economy. Third advantage is ease of start and the cost rates low. Right. So the straightaway to get an ideal power requirement, it is expected that you have to have a steam engine, but employing steam engine in a passenger car is not viable. So that is where the research had gone early days of development of a passenger vehicle. The transmission system is essential part of your vehicle, so along with your engine can take care of the requirement of vehicular power speed characteristics or torque power speed characteristics. So that's what we have understood, and that is why now in this particular class we are going to learn how can we have the design of our transmission system along with your power unit module. This is what is the objective of today's class. Right, if you look at the transmission system along with your engine, there can be a unit called a transaxle. What do you mean by transaxle is your transmission gearbox along with your differential all integrated as one unit, then it is called a transaxle, and that would be witnessed in a front engine front wheel drive vehicle or rear engine rear wheel drive vehicle. Instead, if you have your engine mounted in the front and your drive axle are in the rear, then you have a classical elements that we have looked at in the last class, that a clutch would be there to tap your power from the or the speed from the engine output shaft, and then you will have a propeller shaft, and that would get into a differential, and differential will have a drive axles on the drive wheels of your vehicle at the rear. So this is a conventional transmission system in your vehicle. So today's class, let us look at how can you design this transmission gearbox. So if you look at the gearbox, we'll have n speeds gearbox. In the case of a passenger car, that speeds can be vary from 3 to 5. So you can have a vehicle with the 3-speed vehicle gearbox or 5-speed gearbox at the max in your passenger car. On the other hand, if you look at your heavy vehicles, truck, trailers, all that can go from 5 to 16 different speeds of your gearbox. So what is the basis for deciding or designing these speeds gearbox? So general rule is that you look at the maximum speed requirement of your vehicle to decide on first the highest speed gear that can be appropriately supplied by the selection of your engine. So if I want this is my maximum speed of my vehicle, I would accordingly choose my engine, and that engine output would be direct drive to the drive axle. So that will be the highest speed of my gear. There are vehicles nowadays have got overdrive gears that are going to have surplus power resource in your vehicle whenever it is required to accommodate a sudden wind gust or sudden gradability all to manage. You'll always have some reserve power, and that reserve power is provided by overdrive gear. At that time, if you look at the speed of the drive wheels should be greater than that of the output of your engine speed. So the thumb rule is it can be direct drive for a design of manual system unless and until you are required to have overdrive gears in your drive wheels, right? That's one thing. And first you will select that, and then you will go for the lowest gear selection. So lowest gear selection based on your vehicle gradability on your slope of 33%, 1 in 3% gradability. If you have to go your vehicle, start to go up or reverse direction, you have to come without stalling your engine, and you are able to take your vehicle with full load capacity or partial load capacity, then you are able to design your lowest gear. So that would form a basis for that. So taking these two extremes, then intermediate gears can be designed based on geometric progression with an important thumb rule that an engine at any of the chosen gear should operate in a particular speed range. So if I drive my vehicle in first gear, there will be an operating first speed range of my engine. And second gear, every gear when I drive, I will have to have the same range of speed in my engine. That is the basis for getting an intermediate gears. So this is the base, and I'm going to explain you how are you going to do that. Looking at the requirement first as a higher speed, what is the expression of vehicle high speed given in terms of engine speed, and then sleep and so on. There are expression. And similarly, for the lowest gear, and the last class only we have seen that we look at grade resistance expression, and that is deciding the lowest gear selection. So let us look at today in our class more clearly how a manual gear transmission can be designed for your passenger car, right? So I think I made a picture clear for today's lecture. Let me share my active inspire board for the same. So this is lecture number 38 and we are now on design of manual transmission system. So let me write two important formula first to start our class, right? So the one formula is what is that engine tractive effort that is being provided by your power plant of the engine. So that is tractive effort is provided by engine torque, capital M subscript E refer to engine torque, and epsilon naught that refer to overall reduction ratio of the transmission, including both the gearbox and drive axle gear ratios. That is what is this. And then efficiency of your transmission system, because the power is transmitted to a set of gears mounted on shafts and so on. So there is always an mechanical efficiency associated with that. So that efficiency, if I multiply this all, I'll get an effect net torque overall reduction ratio. So overall reduction ratio is from the gearbox to the drive axle, correct? Whatever is that I get divided by the radius of the rolling wheel. So radius of my tire wheel assembly is what is my tractive effort supplied from an engine. So let's call this is equation 1. So this is equation to be understood first. So in this, what is ME? It is engine output torque. And what is zeta naught? That's overall reduction ratio. What is eta T? It's transmission efficiency, mechanical transmission efficiency or overall transmission efficiency. And then R is what is the rolling radius of the tire, radius of the tire. Tire wheel assembly. Tire wheel assembly. And the second important formula is what is my vehicle speed? How do I get my vehicle speed? The vehicle speed is obtained from looking at an engine speed, small n subscript E refer to an engine speed, multiplied by the radius of my tire wheel assembly, multiplied by 1 minus slip, longitudinal slip ratio. Last class we defined that, right? Longitudinal slip ratio. How do you define longitudinal slip ratio? I is given by R omega minus V by R omega multiplied by 100 into right in percentage. So this is what is I. That is what is called longitudinal slip, analogous to slip angle for lateral force. Longitudinal slip is mandatory to be developed in tire road interaction to get your traction. So 1 minus that slip is what is this multiplied with the engine speed into R divided by overall reduction ratio is what is going to decide my vehicle speed, right? So I should have maximum tractive force for the lowest gear selection. I should have maximum vehicle speed for my higher speed, speed gear in my gearbox, right? So that's what is the two formula that you should remember in always as far as the transmission is concerned for the vehicle. So now let's look at this. So this is what in the previous class we looked at, which is the performance characteristic of gasoline engine. And you see the torque variation would be achieving peak at an intermediate speed. And the engine would start operating not from 0 speed immediately. it would settle at a particular speed, then the operation of engine will be smooth, and that speed is maybe 1000 rpm. In this case, in this diagram, is called an idling speed. So from there the speed increases, the engine operation becomes smoother, and you see the power developed by the engine is increasing to its maximum value, and then it is dropping. And if you look at the maximum torque is not corresponding to the maximum power. So maximum power of the engine is beyond the speed corresponding to maximum torque. So if you look at the maximum power point corresponding speed, after that you see drastic reduction in your torque, right? And you see that the fuel economy point of view, when you have this intermediate speed range, you have good fuel economy that's given by the specific fuel consumption. So what is defined as what is the mass of fuel required for kilowatt hour, unit kilowatt hour requirement of your power is what is given by this. So these are the three things should be looked at, and an advantage of this is high power to weight ratio, good fuel economy, ease of operation, and the low cost is what is an advantage to have an ideal requirement possible by an appropriate gearbox design. That's what in this diagram you look at it. So this expresses the requirement for a vehicular application of the tractive effort as function of speed. And you see that it has to be hyperbolically varying. At low speeds I require higher torque, at high speeds I require lower tractive effort. So how can that be achieved? If I employ my engine, I would have my engine operating at a different speeds like this. In this speed range, I will have my first gear of the transmission would take care of providing maximum tractive effort. As this is what, if you look at the performance of the torque versus speed in the previous graph that we have seen. So we are trying to tap that, and then we will be having an appropriate design of your gearbox. So the first line represents the tractive effort available with the gear reduction, So what is that is maximum possible gear reduction, so that you'll get a smaller speed. And what is this? The last one is no reduction stage, that is direct speed of the engine is obtained, right? That can refer to this. Intermediates are with this. So you will have first gear, second higher, and then no reduction gear stage, right? So if I have this, I can envelope, and that would take care of this. So this envelope should be smoothly operating. That is where the role of a gearbox that comes into picture. So let's look at now the next plot, important plot is this. So here you could see that the effect of gear ratio of highest gear on vehicle performance. So highest gear selection is already I have told it is based on the maximum speed that you want your vehicle to have, vehicle speed, vehicle max speed to be decided. So based on that you would choose your engine, and you look at you will have this plot gives you the engine power requirement is not only to overcome the power required for the resistance on the level road. So this curve and this area refers the power required to overcome the vehicle resistance. But you look at the power characteristic as function of speed, it would be like that. So you have here the maximum power, but you look at your overdrive gears are there, then those would be normally preferred. The maximum vehicle speed is normally chosen beyond the maximum power point of the engine. So you have this, and that would be achieved through an overdrive gears. So you can have 15% overdrive or 30% overdrive, and that would have this reserve power. So my curve become 15% overdrive become, instead of this typical top gear, that's highest gear would be this state gear, right? Whatever the engine output speed, it's straight away taken without any changes. What is this? The solid curve, power variation as function of vehicle speed. And you see the maximum power here, but your resistance somewhere here. So there's some reverse power is there. So if I have my 15% overdrive in my drive axle additional gear, then my reserved power may be reduced, but it can take my vehicle speed further more. So like that, this graph should be Understood. So the area from here to here, this is all area. What is this referring? An additional power resource other than normally what is the power required to overcome all resistances. What are all resistances? High speed, the important resistor, aerodynamic resistance, and your drop or pull, your gradability, but it is on the level ground, so it's mainly your aerodynamic resistance and rolling resistance all overcome with this an additional power. So that is what is that you have to look at. So now let's look at how are we going to design our gearbox. So let me just take the thumb rule for designing. So based on the gear ratio of the highest gear, the gearbox, the maximum speed is decided. So for that, let's look at this expression, eta n. So it is n speed gearbox. So n speed gearbox, eta n refer to any speed. So eta 1 is first gear ratio, eta 2 second. So if it is of 5 speed gear ratio, then it is eta 5 like that, right? So this is equal to, it's decided by what? Maximum. So I am going for first highest gear, that is the lowest reduction ratio, right? Highest gear. First one is for highest gear, that refer to lowest reduction ratio. So the lowest reduction ratio refer to, it can be a direct drive, or if you have an overdrive, it will be more than that. That's what is that the lowest reduction ratio or the highest gear. So that is given by engine speed into radius of the tire wheel assembly into 1 minus slip divided by maximum vehicle speed times axle ratio. So gear ratio of drive axle. So what is this is called? This AX, gear ratio of drive axle. So the rest of the elements you know. So here this is engine speed, and here what is in denominator is maximum vehicle speed. So it is a ratio. So engine speed divided by vehicle maximum speed is what is going to be deciding this. If I consider n equals eta n, it's not eta n, it is not n equals, eta n equals 1. So what I mean by that, if I put here this 1, I get straight away whatever I get it from the engine, that's what is deciding my Vmax. So if I put that, and that would decide my highest gear selection, and that would facilitate to know what is my gear ratio of drive axle, right? So that's going to be NE1 or 1 minus I by Vmax into axle. So that gives me drive axle ratio would be NE1 or 1 minus I by Vmax. So engine speed multiplied by R into this by maximum vehicle speed is what is equal to this. My drive axle gear ratio I can find out by considering 1. Right? So if I have overdrive of 15%, then I will take instead of 1.15 equating, and then I will get what is my gear ratio of drive axle like that. So this is how I can find my highest gear in a gearbox with n speed. So this, what is this? Zeta n, it refers to highest gear ratio of the highest gear ratio of the highest gear. If my vehicle is a 4-speed gearbox, then it is zeta 4, right? So so this is the basis to decide what is my vehicle higher speed. So if I have this vehicle high speed, then I would decide my next speed from this ratios. What is this ratio? Look at like this. In the last class itself, we have seen for the lowest gear. So let us do that. Then I will go for showing you how the intermediate gear speeds can be decided. I will explain that time. So the gear ratio of the lowest gear, right? So for gear ratio of lowest gear in the gearbox would be obtained how? Based on this. So that would be obtained based on W sine theta S max, maximum slope. So a vehicle with full load to negotiate 33% grade would be the basis for deciding the lowest gear. Or at that time your vehicle running at higher speeds, say around 90 kilometers per hour if I drive, my vehicle should be able to clear my grade, gentle grade of 0.3%. So I should have a small slope at that time. If it is a 33% slope, then my vehicle speed should be smaller. At the lowest speed, I should have a maximum tractive effort. So that's what is going to decide. So for that to accommodate, I would consider this as basis for deciding my lowest gear ratio. So this would be given by we have looked at, say, let us consider for time being rear wheel drive vehicle. So in rear wheel drive vehicle, we have derived our maximum tractive effort expression mu p times w into L1 minus Fr into h by L, all divided by 1 minus mu p h by L. So this is what is that expression we had, minus Fr times W is what is the expression in the last class we looked at. So my zeta 1 to get, I have to take this on this side. So this is my, this expression is what is the maximum tractive effort that would be possible in a rear wheel drive vehicle. And that is equivalent to accommodate the grade resistance plus the rolling resistance. So it comes on this side, and that has to be taken care by gear. So what I have to do, how do I decide my zeta 1, the lowest gear? That would be equal to W into sine theta S max this plus FRW. This is all divided by what is that comes from the engine. So what is that comes from the engine? We have looked at the previous expression here, this expression. This expression number 1. So this is what I get it from engine. So I have to divide this with this engine torque, and this. So this force, this is from engine. So I have to divide that by equation number 1. So I will have here this expression here, ME engine torque multiply ME what? ME max, maximum torque, and then drive axle ratio and efficiency divided by R, that goes up, and then numerator R. So this is what is going to decide my lowest gear ratio in my rear wheel drive vehicle. If it is front wheel drive vehicle, the expression would be changed here, that you know, right? So now, having found this zeta 1 and zeta n, let us look at how intermediate gears, that gear 2 and 3 are decided in a 4-speed gearbox, is what I am going to explain now. So for that, let's look at this diagram. Let me take vertical axis, engine speed. On a horizontal axis, vehicle speed. So horizontal axis, what is my vehicle speed required, and vertical axis, what is my engine speed required. So what is that common rule for deciding your intermediate gears is geometric progression is followed, and importantly, the engine has to operate. The range of engine speed should be same for all the gears that you are having it. So now we have got a maximum speed decided. So what I will do, I will take my maximum vehicle speed first on this horizontal axis. So that will be V4 in case of n is equal to 4 gearbox. So 4-speed gearbox, I have my V4 obtained from my maximum vehicle speed expression. And that speed is what I would take now, achieved by an engine operating in a decided speed range. Decided speed range. So this is one line, that is engine speed, and this is another line, NE1. So NE1 is what is taken in the expression. So this is my engine speed, and that engine speed getting the same speed for all the gears is not possible. So the basis for intermediate gear, I have a range of gear engine speed. So range of engine speed means it's not a very long range, it's a smaller range, and I decide, and that has to be there in all the gears, and then I would project this line up, so that now I have here this ratio of range is decided based on geometric progression. I just explain you now, right? So this is this range is what engine operating speed range. How this range is determined is what I am going to explain you now, and that is where we follow geometric progression and commercial vehicle design. Whereas in passenger car, it is not exactly geometric progression followed. Rather, at high speeds, the expectation of a vehicle speed operation. In city range driving, I always to have my gear shifting from highest to the next to the highest and the lower side. So I will be operating my vehicle speed between the top two gears, either in fourth gear or fifth gear or third gear only. I will not come on highways, unless and until I have to go to closer to very small speed and then start my vehicle. I will not go for, unless I have to go for sudden braking, jamming on that. No, I will not get my gears to the lowest gear. So there are some rounding off. The procedure is different. But however, the trucks are considered heavy vehicles. The intermediate speed or the operating speed range of your engine is decided based on geometric progression. That I would be considering even now for this vehicle model. So it is all for 4-speed gearbox. So if I look at my second gear ratio to the first gear ratio, that should be same. That's what is that geometric progression. So if I take now third one, the ratio of second one is same. If I take fourth speed gear reduction ratio to that of 3 is same, and I can call this should be obtained through an engine operating speed NE2 by NE1, and that is constant kg. So this ratio should be constant. So if I have successive gear ratios, zeta 2 to zeta 1 or this, whatever that I have in my 4. So if I have my higher speed, fifth 5 gear speed, then I will have zeta 5 by zeta 4. And that ratio should be constant, and that ratio decides my engine operating speed, NE2 by NE1. So if I have this, that is what is this constant ratio. And this constant ratio kg can be now expressed by this of cubed root, because there are 3 ratios here, cubed root of zeta 4 by zeta 1. So highest gear to the lowest gear ratio cubed root is what is going to give me this operating speed range of my engine for 4-speed gear box, right? Or I can also rewrite this as, if I have to go in for n speed, like the 16-speed gearbox for a commercial vehicle, the same procedure can be extended. I would have my kg in that time would be obtained by n minus 1, ng minus 1, the root of zeta n by zeta 1. So I will have like this ratios written, and final zeta n to zeta 1. How many ratios that I have? 4 gears with 3 ratios, 5 gears, 4 ratios. So if it is n minus 1 to the root of zeta by zeta 1 would give me this speed ratios. So I can rewrite this understanding once again as So what is this ng here? This small subscript g is the number of speed in gearbox. Right? So if this is so, you would be able to have now zeta n is given by kg into zeta n minus 1. So look at this n minus 1. So if this is 4, this is 3. So this is all simply generic form it is represented. So if you have understood this geometric progression technique followed, then I know what is my Ne2 by Ne1. So is kg. So this decides now my this line. So if I have my Ne1 and Ne2 by Ne1 ratio would decide what is this speed now here, right? So, so this speed is obtained for the highest. So this is for the highest corresponding to the highest vehicle speed. So Ne2 I get it how this into kg. So Ne2 is kg into Ne1. Ne1. And then I have this. So wherever it intersects this, I should connect that to this point, origin, and draw this line diagonal. So now this is going to intersect this Ne2 line, horizontal line, and that you drop down here again, or you go up there. So that's going to decide my third speed. That's my V3 now, here, V3. So between V3 and V4, you see this is that range that is operating. So now where it is intersecting this Ne1, which is my direct engine speed. Sorry. So that's here. And again, you connect this to this. And where is that intersect this line is going to decide my V2 speed. And then you connect this point to this. And where is that? It's going to intersect. That's going to give me V1. V1. Right. So now what is that I have here is this is my first gear speed. So first gear would take care of this range. When I drive my vehicle in first gear, the vehicle speed can go up to V1. At that time, my engine, right, from till here, this can be next to be speed V2 when I go. My gear should be second gear. This is second gear from here to here. It is second gear. So at that time, you see the engine speed can be between this in this range only. The range of operation here for every gear is the same. That's what here I would like to emphasize and say. So this is V4, V3, V2, V1. Yeah, that's correct. And then from here to here, this is third gear. And this is my fourth gear. Fourth gear. Any doubt in this? Any doubt in this? If you do not have any doubt, so this is all your thing. So let me now put you some of the data, gearbox for passenger car some table and for truck some table to conclude our today's class. To look at how those speeds are obtained, right? So just let us look at these table. I'll just get it from the textbook for you now. So for this topic, please refer to Wong textbook, Theory of Ground Vehicle, right? So look at this graph. So you have, look at this table, you have your gear ratios of transmission for commercial vehicle. So you can see here there are different vehicle with a different number of gears. So you have a vehicle with 6 gears, vehicle with 8 gears, vehicle with 10 gears, 13 gears and 16 gears. So the value of kg calculated from this equation 3.29. What is that equation is only this. So kg is obtained by nth root of n minus 1 zeta n by zeta 1. So this formula is what is used to get this. And once you have that and using this ratio, see this is your final one, your other gears reductions are obtained. So 3 is what is the first gear reduction. So if my engine output is 3000 RPM, then it would be divided by 3 and appropriate efficiency, all that comes. So like that you should understand here. So these are all my intermediate gear ratios. So what is this? This is zeta 1, the zeta 16. So if I have so this is all the gear ratio. So here this is gear ratios, it corresponds to zeta 1 to zeta 16 of this vehicle. And similarly you also have, and here you can see this exactly following the geometric progression. What I mean by that, if I take this ratio, what is that, zeta 6, first case you take this Elizon HT70 vehicle gearbox if you take. So these are the brand gearboxes, right, in a commercial vehicle. And if I take zeta 6 by zeta 1, zeta 5, what is that is ratio? 0.76 by 1. So it is 0.76. So this is the ratio. So if I take zeta 5 by zeta 4 of the same case, that is 1 by this. So 1 by 1.31. So that is again going to be 0.76. So like that, it's what is this subsequent sequence. So zeta 2 by zeta 1 is what? 2.28 by 3. So that's going to be 1.14 by 1.5. That's again going to be 0.76. So like that, it is followed geometric progression. So here it is 0.85 by 1, 1 by 1.22, 1.22 by 1.44. If we take, that would be in this ratio. So this is the basis for deciding an intermediate gear ratio. Right, so intermediate gear ratio, why do I have to choose? I have my expression now like this, right? Vehicle speed, overall reduction ratio when you are writing, vehicle speed at any time will be what? Engine speed R into 1 minus I by zeta overall. So this overall is which gear I am driving. If I am driving my vehicle in my 6th gear commercial vehicle in 4th gear, then I will have, this is to be substituted here with an engine speed known, right? And I will have my vehicle speed. What is that vehicle speed at that time? So like that, I should have to look at this thing. Or if you are looking at, I drive my vehicle, I apply my diesel rate accordingly to the situation, then I have to shift my gears. So I have to get my gear from the highest gear as I decelerate down. So how do I decide? Based on this speed. So what is that speed I have reduced? If that comes and I bring that down, I know what is this, and that should be falling accordingly to this intermediate gear ratio. So that is how this gearbox function. Right. So I hope I have explained you the basis of design of manual gear box design. First to be consider highest speed requirement of your vehicle and an appropriate engine selection, and then you will go for this intermediate gears through geometric progression, and you get your kg and decide your engine operating speed, and then any one and any two is get obtained. So join your origin 0 speed line point to the draw the diagonal, and then where it intersect the lower range of your engine speed. Lower range of your engine speed is this. This. Where is that intersect? So this point, and that has to be considered as the second speed. And then again connect to this, and where it intersects, that is in V2, V1, like that we have to get your speed ranges, and that gives you what is the speed range accommodated by this gear. So how do you map this to this graph? What is this graph we can now look at, and you would appreciate how that is achieved. So here is this. This one. So the first speed, if I take from here to here, this speed range is by first gear. So next speed range is this. Next speed range is this. Like that, from this you are able to get your speeds, right? So this is enveloping. So first gear envelope and next. So you will be able to map that the different speeds of these gears brought in with this, right? Okay, so with that note, let me just stop today's class of finishing this. Then now we will move on to brake system of our vehicle in the next class, right? On Monday we will start with braking performance of your vehicle. So of course, in tractive performance of a vehicle, we also have to solve some problems. Please look at your WOM textbook, where you are expected to get your what is the maximum acceleration that can be developed for the vehicle to overcome various resistances. Or so there are example problem. Please go through them, solve those things that may be asked in your examination, right? So with that note, let me stop today's class. If you have any doubts, you can ask. Otherwise, I'll stop recording.